Of the 117 elements known so far, only 11 are in the gaseous state at room temperature and pressure. The gaseous state is the simplest form of matter. This is why all gases show almost identical physical behavior regardless of their chemical nature. They are characterized by the following properties. Gases have no definite shape and volume, and hence assume the volume and shape of the container. Gases are highly compressible, which means that when the pressure increases, the volume of the gas decreases. Gases exert equal pressure in all directions. Gases intermix equally and completely in all proportions without any mechanical aid. Gases have lower density than solids and liquids. The behavior of gases is governed by gas laws, which define the relationship between measurable properties such as volume, V, pressure P, temperature T, and the number of moles N. These properties are interdependent and describe the state of the gas. The four main gas laws are Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Boyle's law expresses the relationship between volume and pressure. Charles' law expresses the relationship between volume and temperature. Gay-Lussac's law expresses the relationship between pressure and temperature. And Avogadro's law expresses the relationship between volume and number of molecules of a gas. Let us discuss each of these laws in detail. In 1662, Anglo-Irish scientist Robert Boyle, after conducting various experiments, concluded that at constant temperature, the pressure of fixed amount of gas is inversely proportional with its volume. This is known as Boyle's law. Mathematically, Boyle's law can be written as P inversely proportional to V at constant temperature T and number of moles of the gas N. Or P is equal to K by V, where K is a proportionality constant, whose value depends on the temperature and number of moles of the gas. On rearranging the equation, we get PV is equal to K. Or, in other words, at constant temperature, product of pressure and volume of fixed amount of gas is constant. For example, if N moles of a gas A occupying volume V1 at pressure P1 expands to volume V2 and pressure P2 at constant temperature, then P1 V1 is equal to P2 V2, which is constant. Now consider N moles of gas B at pressure P1 and volume V1. Let us now slowly increase the pressure, keeping the temperature constant at T1. We observe that volume of gas decreases as the pressure increases. If we plot this variation of pressure versus volume on XY graph, we get the given curve. Let us now change the temperature of the gas to T2 and repeat the same process by keeping the temperature constant at T2. In this case, If we plot the variation of pressure versus volume, we get a different curve. From this, we can conclude that each pressure versus volume curve corresponds to a different constant temperature for a given amount of gas. These curves are known as isotherms. Similarly, we can plot variation of pressure against 1 by volume. We get straight line for each constant temperature. These straight lines pass through the origin. The next law is Charles' law that describes the relationship between volume of a gas and its temperature. Jacques Charles and Gay-Lussac studied the relationship between volume and temperature of gases independently. They concluded that for a fixed mass of gas at constant pressure, the volume of gas increases with increase in temperature and decreases on cooling. They found that when pressure remains constant, a fixed mass of any gas expands or contracts respectively by 1 by 273 of its volume at 0 degrees Celsius for every rise or fall in temperature by 1 degree Celsius. Let's understand this through mathematical expression. Let V0 be the volume of a fixed mass of a gas at 0 degrees Celsius, and let V be its volume at temperature T degrees Celsius at same pressure. Then, volume V at temperature T is equal to V0 plus V0 divided by 273 into T. Or V is equal to V0 into 1 plus T divided by 273. Or V is equal to V0 into 273 plus T whole divided by 273. Let this be equation 1. We know that T plus 273 is nothing but absolute temperature in Kelvin scale. Writing T plus 273 as T, we get V is equal to V0 into T divided by 273. But for a given mass of a gas, V0 by 273 is equal to constant. Therefore, V is equal to kT, where K is a constant. Remember, temperature T is in Kelvin scale. This is a mathematical expression for Charles' law, which states that the volume of a fixed mass of a gas is directly proportional to its absolute temperature if the pressure is kept constant. If a given gas occupies volume V1 at T1 temperature and volume V2 at T2 temperature, then by Charles' law, V1 by T1 is equal to K constant, which is in turn equal to V2 by T2. Therefore, the equation can be written as V1 divided by T1 is equal to V2 divided by T2 is equal to K. This is called the Charles' law equation. For a given amount of gas, if we plot the variation of volume versus temperature at different pressures, we get different straight lines corresponding to each pressure. These lines are called isobars. You can observe all the straight lines on extending to zero volume, intercept the temperature axis at minus 273.15 degrees Celsius. From the graph, if we substitute the value of temperature as minus 273 degrees Celsius in equation 1, then volume at minus 273 degrees Celsius becomes 0. Thus, we can conclude that the volume of a gas would be reduced to 0 at minus 273 degrees Celsius. The temperature minus 273 degrees Celsius is called absolute zero. This is the lowest temperature that can ever be reached. At this temperature, the molecular motion of gases will stop and will cease to exist. The next law is Gay-Lussac's law. According to Gay-Lussac's law, at constant volume, pressure of a fixed amount of gas varies directly with the temperature. In other words, at constant volume, temperature of a gas increases with increase in pressure and decreases with decrease in pressure. Mathematically, Gay-Lussac's law can be written as P is directly proportional to T, or P is equal to kT, where K is the proportionality constant. The numerical value of the constant K depends upon the amount of the gas taken and the volume. This law can also be derived by combining Boyle's law and Charles' law. If we plot pressure versus temperature for a given volume of a gas, we get straight lines corresponding to each volume. These lines are called isochores. The fourth gas law is Avogadro's law. In 1811, Italian chemist Amedeo Avogadro stated that at same temperature and pressure, equal volumes of gases contain same number of molecules, irrespective of their chemical and physical properties. For example, consider 1 liter of hydrogen gas and 1 liter of oxygen gas. Then, according to Avogadro's law, at same temperature and pressure, both 1 liter of hydrogen and oxygen contain equal number of molecules. Mathematically, Avogadro's law can be written as V is directly proportional to N, where V is the volume of the gas and N is the amount of gas or number of moles of the gas. Replacing the proportionality sign by proportionality constant K, we get V is equal to Nk.